Hello guys, so till now we have studied about the means the thermal resistance and thermal resistance is when connected in series and when connected in parallel. Also the concept of thermal resistance we have studied till now. So now we will find the temperature distribution in simplified cases. So temperature distribution for simplified cases now we will see. So first we will see the infinite plane wall. So before that we have to make certain assumptions, because as I'm again and again saying that we are looking for simplified cases, what for that what are the simplified assumptions? Okay, first thing is one dimensional heat flow. Okay, one dimensional heat flow, or if it is a spherical or cylindrical body, then it is radial heat flow. Okay, the next assumption we are making is the heat flow is steady state. Steady state is maintained while the heat is transferring through the body. Okay, and there is no internal heat generation. There is no source of heat generation inside the body. No internal heat generation. Fourth is material is homogeneous and isotropic, means K is material is homogeneous and isotropic. It means that Kx, Ky and Kz are both same and we can take it as K. So it means that thermal conductivity is independent of the direction in which it is measured. Okay, so it means K value is constant, and we are saying that K value is not function of temperature. K value is constant. Okay, material is homogeneous, means it is no, and isotropic, it means K is not dependent on direction but can be dependent on temperature. But in the fifth assumption we are saying that K value is constant, and by saying that we means that K is not function of temperature. So this is the assumption. And since we are considering one dimensional heat flow and we are assuming that both the surfaces are maintained at different temperature, are maintained at different temperatures. Okay, so let's start with plane wall. Infinite plane wall or infinite slab, also we can call it infinite plane wall, right? So what is the meaning of infinite plane wall? Infinite plane wall, we can give example like our wall of the building. It will look like this. Let's say this is the width, this is the height, and this is the L, and suppose this is the coordinate x equal to 0 and this is x equal to L, and we are saying that these two surfaces are maintained at different temperatures. Let's say it as T1, T2, and we are assuming T1 is greater than T2, and because of that, what will happen? Heat will flow, right? Heat will flow in this direction from high temperature to low temperature, and our objective is to find the temperature at any location x from this surface. Okay, so we will start from the governing equation. Okay, so infinite plane wall. First, infinite plane wall means that the thickness is very less than the other two dimensions. This is the meaning of infinite plane wall, right? The direction in which heat is flowing is very lesser than the other two dimensions. Okay, so let's start with the governing equation to find the temperature distribution inside this. Since it is steady state and k is constant, we can write for one dimensional case like this. Okay, and there is no internal heat generation. See this assumption, third one. So this term will go to 0, and since it is steady state, so this is also will go to 0. So since temperature only one variable is there, so we can convert it into ordinary variable. This partial derivative will become ordinary derivative since it is function of x only. Okay, then if we integrate it twice, we can get c1x plus c2, and c1 and c2 are the arbitrary constant which can be found by the boundary condition. So we have boundary condition. First is at x is equal to 0, temperature is T1. So substituting that, we get C2 as T1. And second boundary condition is x is equal to L, T is T2. And we can find T2 as C1 times L plus C2 is T1. So we can find C1 as T2 minus T1 divided by L. Putting these two values of C1 and C2 in the equation 1, we can have this distribution. We can see that temperature distribution is linear inside the plane wall. Okay, so we can draw the temperature profile like this. At x is equal to 0, temperature is T1. At x is equal to L, temperature is T2, and we can draw a straight line between the two. So we can write like linear temperature profile. Okay, so if we substitute x is equal to L by 2, we can get the temperature at half of the length. Okay, and x is equal to L by 3, we can find temperature at any location x. So in the next part we will see about the cylindrical system. Thank you.